In my Structural Engineering Made Simple series, today I talk about computing cross-sectional properties in steel built-up sections. Please take a moment and read the disclaimer at the bottom of this slide before we continue. Built-up sections are made up of structural steel profiles, including plates, that are welded together to make stronger beams and girders. In some older designs, and especially in railroad bridge applications, sections made up of profiles riveted together have also been built. These are some examples of built-up sections: a plate girder, plate and angles, and a channel and I-beam. Cross-sectional properties that are often needed for beam design include the location of the centroid of the cross-section, which is at a distance y bar from the extreme bottom fiber of the cross-section. As you can see in here, the location of the centroid is shown with y bar. This location is where the static moment of the upper portion of the section is equal to the static moment of the lower portion of the section. The cross-sectional area A, the moment of inertia with respect to the x axis, which we call it Ix, and the section modulus Sx for the top and for the bottom. Also the radius of gyration Rx. Occasionally, we may need to find the moment of inertia with respect to the y axis, which we call it Iy, and the corresponding section moduli and the torsional constant J. We talk about these a little bit later. Cross-sectional properties of several common shapes are provided below. This information is helpful in computing the cross-section properties of built-up sections. The centroid axis is shown is XX. For a rectangular section with the dimensions B and H, the moment of inertia with respect to the x-axis is BH cubed divided by 12, and of course the cross-sectional area is B times H. For a triangular section with respect to its own XX axis, which is at h over 3 from the base, the moment of inertia Ix is BH cubed over 36, and cross-sectional area is BH over 2. For a circular cross-section, with respect to x-axis, the moment of inertia Ix is pi h4 divided by 64, and the cross-section is pi h squared over 4, where h is the diameter of the cross-section. Please notice that this equation for Ix is with respect to xx. Do not mistake this with the polar moment of inertia, which is with respect to the center of the circle. For the case of standard profiles such as angles, channels, W and S section, please use the AISC manual. For the area and the moment of inertia, as well as the location of the centroid and other cross-sectional properties, here are some examples. You look at an equal leg angle here, for which from AISC we find the following values. It's always important to list all these values. For example, for an angle 6 by 6 by 7/8 of an inch thickness, the moment of inertia with respect to x and with respect to y are equal. 31.9 inches to the 4. The area is 9.75. And you notice two dimensions EY and EX. They are representing the location of the centroid. EX in this case is equal to EY, and each is equal to 0.813 inches, because this is an equal leg angle. These two dimensions are important when we compute the moment of inertia of built-up sections made up of angles. Here you see a channel. Again, you notice that the YY has a distance EX from back of the channel. However, notice that in the XX, we have a symmetric section. For a channel 8 by 18.7, we have the moment of inertia for X as 43.9, moment of inertia for Y as 1.97, area as 5.51, and that dimension EX is 0.565. Again, this information is important if our section is made up of channels. Location of the centroid axis and the computation of the cross-sectional moment of inertia and area require several steps. First, you divide the section to many segments. Each segment will be either one of common shapes, for example, a rectangular, or one of standard section profiles. Establish a reference line, usually the base of the section, for computation. However, note that if the section is symmetric, it is a good idea to take the reference line at the centroid axis. Prepare two tables, one for computing the location of the centroid and another one for computing the moment of inertia. Recall that the moment of inertia for a segment I with respect to any axis XX, capital X, which is parallel to the segment's own axis, little x, is obtained as follows. I, capital Xi, is equal to I, little xi, plus the area multiplied by the square of a distance between the two axes. I, capital Xi, is the moment of inertia with respect to the capital XX axis. I, little xi, is the moment of inertia with respect to little xx axis. These two axes are parallel. And the yi is the distance between xx and xx, and ai is the cross-sectional area of the segment. This is an important equation to remember. The location of the centroid is simply equal to sigma ai yi divided by sigma I. Well, sigma in here refers to the summation of all the segments. In other words, we are talking about sum of the static moments with respect to the baseline divided by the total area of the cross section. And the moment of inertia for the entire section is a summation of the moment of inertia of the individual sections with respect to the centroid. And that is where this equation comes from. And of course, the total area is sigma ai. And if there is a hole in the cross section, for example, in the case of riveted or bolted sections, when there is a portion of the section is cut out, you consider the hole as a negative area with a negative moment of inertia in your summation in this equation. The radius of gyration is the square root of ix divided by a, and the section modulus with respect to the bottom fiber is ix over y bar, and with respect to the top is ix divided by h minus y bar, where h is the height of the cross section. Let's look at some examples. In example number 1, we have a section made of two plates welded together. The bottom plate is a 6 by 3/4 of an inch thickness. The vertical one is 4.5 by 1/2 an inch. As you expect, the location of the centroid is closer to the bottom plate, and we call the location as y bar. In order to determine the location of y bar, we divide our section into two segments. There are only two segments here, and we form our first table. Here is our first table. Let's look at it. In the first line, I have listed what kind of segment is involved, what is its cross-sectional area, which in this case is 4.5 by 1/2 an inch, is 2.25. What is its distance from the extreme bottom fiber, which is our reference line? If you look at it here, is half of the height of the bar, so 0.5 times 4.5, plus the thickness of the lower bar, the thickness of this bar. That would bring us to the reference line in here. So that is 3 inches. You multiply 3 inches by 2.25 and the answer is 6.750. That is the static moment. The bottom flange is a horizontal bar as you see here, 6 by 3/4 of an inch. We find the area. The location of its center from the reference line is only half of its thickness. And when you multiply these two values by each other, you get the static moment 1.688. Adding these two values gives me the total sigma AI yi, and the total area, of course, is 6.75. So when I divide this value by this value, which is the area, that gives me the location of the centroid. Now for computing the moment of inertia, we form the second table. Here is a second table. Some of the information from the previous table has been transferred to this one. Again, our vertical plate, the area we found 2.25. Now notice that here we have y bar minus yi, because that appears in our equation. So simply take the y bar that you find before, deduct from it the yi, and don't worry if you get a negative value, because eventually this goes to the power of 2 and becomes positive. And then you compute the moment of inertia of the section with respect to its own axis, which is somewhere at the middle of the section. And that's a rectangular one, so it is b h cubed over 12, so we get 3.8, and then put them all in this equation. So for segment at the top, the vertical one, we get 10.771, and that is with respect to the capital XX. Now we do the same thing for the lower plate. That's put here horizontally, so the area is 4.5. And again, 1.25 minus the value we had from previous table, which is the location of the center of this plate, and we get 0.875. Now notice that the moment of inertia for this plate is very, very small because it is laid flat. So it's 6 multiplied by the thickness divided by 12, and it's only 0.211. You can put it in the equation, area multiplied by the distance we computed, and we get the value equal to this. Now, therefore, this is a total moment of inertia. So, in a summary, our moment of inertia is 14.427. And since we are looking for the section modulus, take the moment of inertia divided by y bar. That's 11.542 inches to the third. That's with respect to the bottom fiber. And h minus 1.25 appears in the denominator in the second for x for the top. And remembering that h is a 4.5 plus the thickness of the bottom plate, which is 5.25. And we get the section modulus as 3.607. This is the more critical one that would be used in design because it is a smaller value producing larger stress on the cross section. Now how about the radius of gyration? That's the square root of ix over a, which turns out to be 1.46. Let's look at another example. In this case, we have 3 plates, 8 by 1/2 an inch at the top, 10 by 3/8 of an inch as the web, and 5 by 1/2 an inch as a bottom flange. So what we do is that we again form our first table to find y bar, and you expect that capital XX would be closer to the top because there is more area in there. So we put our first table together, again as before, the top flange, flat plate, area, location to the reference line, which is here. So you get the center of this bar all the way to this place. So you get half of the thickness of the top plate, the entire depth of the web, and the thickness of the bottom flange. So you get 10.75, and you get a static moment 43. For the web, which is a 10 by 3/8 of an inch, the area is 3.75, and it's 1/2 of its height plus the thickness of the bottom plate, Multiply these two terms again by each other, you get 20.63. And the bottom plate is flat, so it's only at quarter of an inch from the bottom, from the reference line. The static moment for this one is pretty small. When you add these three, you get the total static moment. When you add the areas, you get the total area. So how do we find y bar? Just divide the total static moment by the total area and you get 6.27. So now for the moment of inertia, we put our second table together. Part of the information is coming from previous table. Notably is that here you find y bar minus yi. This is important. Again, some of these terms become negative, but that's okay because eventually go to the power of 2 as you see here. This plate is flat. You notice that its moment of inertia is pretty small. Nevertheless, it produces a very large contribution to the total moment of inertia. The web is vertical. We find the corresponding y bar minus yi. The moment of inertia with respect to its own axis is larger. Put it in the equation, turns out to be 37.3. The bottom plate is a flat plate again. And again, you find the y bar minus yi. The moment of inertia is extremely small, and plug it into equation. Nevertheless, the effect is pretty large because of this term. So when you add the 3, you get a total moment of inertia. So in summary, we get our moment of inertia. The section moduli are obtained pretty much the same way as before, knowing that the overall height is 11 inches, 10 inches for the web, half an inch for the top plate, half an inch for the bottom plate. And again, notice that in this case, we have h minus y bar here and y bar in here. Turns out that with respect to the bottom, we have a much smaller section modulus, which is more critical. And again, our radius of gyration is computed accordingly as 4.51. Our example 3 is a built-up section made of 4 angles and a plate. Now, although in appearance it looks complicated, actually it's very simple. Why? Because it is symmetric with respect to xx, and any time that your section is symmetric, is a good idea to take your reference line exactly at the location of the centroid. We know that y bar is 1/2 of the overall depth of the section, which is 23, so divided by 2, you get 11.5. Each angle is a 6 by 6 by 7/8 of an inch, and the plate is 23 by 0.5 inches. That's where this 11.5 comes from. All right, so we don't need the first table, but we need to get the information for this angle from the AISC, and we list those things from the AISC table. And now here I'm also showing the shape of this angle. Recall that EY, which is 0.813. Now we see how this EY gets into the picture. So we only have one table, and that's for the moment of inertia. We have 5 segments, we call them 1 to 4. Each of those is an angle, and therefore the total area is 4 multiply area of one angle. Y bar minus yi is 11.5 minus 0.813. Where did I get this from? That came from the AIC table. And then the moment of inertia of the angle with respect to its own axis from the table is 31.9. We plug everything in this equation, and you notice that the contribution of the 4 angles is quite a bit. You notice that I put a 4 in front and just wrote the information for one angle inside the brackets. That's it. Next we have the web, which is a vertical plate, and this one has an axis over here which is exactly coincide with the overall axis of the cross section. Therefore that distance is equal to 0. The contribution of the moment of inertia is only from this plate itself. We don't have that second term. You notice that this value is exactly the same as that one. Well, because this is equal to 0. All right. So add the areas. add the moment of inertia, and there you are. Therefore, the moment of inertia is at 5088.9. Area is 50.5 square inches. Sx at the bottom is exactly the same as at the top and is 442.5. And the radius of gyration turns out to be 10.04. Torsional constant. Occasionally, we need to find the torsional constant, especially when we do torsion and warping effects analysis for beams. For standard profiles, we can refer to AISC. The values of the torsional constant J are listed. However, if you have a plate girder, remember that plate girder is an open section, you can use the following approximate equation for computing J. This summation in here refers to the number of rectangular segments in the section, and X is the thickness of each segment and Y is the width of the segment. So you divide the entire section into rectangular ones, and each one has a very small thickness. However, it might have a very wide width. The width is equal to Y. The thickness, you can take it as X. Now you may have a built-up section which is in the form of a box. If it is a closed form section, and in general you might have a dimension A by B, the thickness as TB on the top and bottom flanges, in the web as TA and TA, then you can use this equation. So this is the equation that you can use for computing J. Is 2 times the thicknesses of the two parts, A minus TA, that's A here, minus TA to the power of 2, B minus TB rather to the power of 2, divided by ATA plus BTB minus TA squared minus TB squared. Now, occasionally, you may have a section that is cut, has a slit in it. It looks like a closed section, but it has a cut. In that case, it is not a closed section anymore, and you can find J from this equation. 1 over 3 little p times T to the 3. T is the thickness of this thing, and little p is a perimeter of this area which is shown with red. So that goes through the midsection. You draw this line through the midsection, and then find the perimeter of this area, put it in this equation, and you get J. Now let's look at an example. Let's look at our example 2, and let me show you the figure for that one. Remember that 3 plates, and we want to find the torsional constant. Again, we use our sigma equation. There are 3 segments, 1, 2, 3, and each one you use this equation. The width multiply thickness to the power of 3. Very simple. You get 0.717, and don't forget the total value is finally divided by 3 when you add these things. With the formation of the 2 tables, as we mentioned, the procedure for computing the section properties becomes simple and straightforward. Please note that if the moment of inertia with respect to y-axis is required, you can follow the same process. However, the section will be rotated by 90 degrees. Thank you for watching this video.